everyone. In this video, we will be continuing with where we left in the previous video. In the previous video, we were talking about potential flows, and potential flows being the solution to the Laplace equation. And the Laplace equation, since it is a linear equation, different solutions can be superimposed in order to create further solutions. And the motivation behind this is that we want to combine different flow solutions to create further flows. So for example, if we have two different flows, we can put them together and get a third flow which is different from the first and the second flow, and this can be done by mere addition of the solutions. If we have the flows which we call as the elementary flows, our hope is that the elementary flows, on adding to one another, will result in more complicated flows, which are more physical world like flows, real world like flows. So keeping that in mind, we have dealt with one such elementary flow, which was the uniform flow. In this video, we will be looking at another very important elementary flow, which is called the source and the sink flow. The source flow looks like this. So I have a point O, and from this O, the fluid is emanating radially outwards. So this is called the source flow. And as you might have already guessed, a sink flow is where the fluid, instead of emanating from a point, comes radially inwards and disappears at the point O. That would be a sink flow. So now let's look at some mathematics behind this source and sink flow. So the most convenient coordinate system to work with in this context would rather be the r theta coordinate system, or the polar coordinate system. So what do I mean by that is the radial distance would form one coordinate r, and the other coordinate would be the angle theta. So we will be using this coordinate system to analyze this flow mathematically. So let's say the velocity vector can be decomposed into two components, which is the radial component Vr Er cap, where Er cap is the unit vector in the radial direction, plus V theta E theta cap, where E theta cap is the unit vector in the theta direction. So from the figure, this figure, it's pretty evident that the velocity vector does not have any component in the theta direction. So we can straight away say that V theta is 0. There is only an r component for the velocity, and we need to find out what this r component is, right? So for that, we need to resort to the continuity equation. So continuity equation says that the divergence of velocity is 0. So the divergence of a vector in the r theta coordinate system is given by 1 by r dou by dou r of r Vr plus 1 by r dou by dou theta of V theta. This is del dot V in the r theta coordinate system. Now we already know that V theta is 0, hence this term goes to 0. The other term that we are left with is this one. As you can see, if the divergence has to be 0, this term too has to be 0, and for this to be 0, r Vr should be independent of r. so that the partial derivative with r goes to 0. Hence, we can say that Vr should be some constant divided by r. So on plugging this into this, what we get is dou by dou r of r into c by r, which is 0. So let's look at how we can find what this constant c is, right? So let's say, let me just erase this part. So let's say I have a source flow placed at the origin here, and I have the fluid emanating from this point. Let me take a circle around this point, and let's say the circle's radius is r. So the mass flux through this circle can be written as integral, because I have to integrate this over this entire circle. So that becomes integral Vr rho into the area, the elemental area, which is r d theta, and I'm integrating this over the entire circle, so this becomes 0 to 2 pi. So on integrating this, we know that Vr is c by r, so this becomes 0 to 2 pi rho c d theta, which is equal to rho c 2 pi. From here we get c is equal to m dot by 2 pi rho, and I would like to call this m dot by rho as capital lambda by 2 pi. This capital lambda is generally called the strength of the source or sink. So finally we get the expression for the velocity components in a source flow. So let me just write that down. Vr is lambda by 2 pi r and v theta is 0. Now let's look at the velocity potential and the stream function of this flow. So the velocity potential phi in the r theta coordinate system is given as dou phi by dou r is Vr, and dou phi 1 by r dou phi by dou theta is v theta. So let's look at this equation first. So dou phi by dou r is equal to lambda by 2 pi r, and on integrating we get phi is equal to lambda by 2 pi ln r plus f of theta. Because it's a partial derivative, right? So now let's look at the second equation. The second equation gives you nothing, because v theta is 0, so you can only say that phi here is going to be a function of r. And on combining these two, what we get is phi is equal to lambda by 2 pi ln of r. So the similar approach can be used for finding the stream the stream function, and that I leave it to the viewers. I can give you the formulae for that. You can also find it from any of the standard textbooks. Anderson is a good textbook for these concepts, so one may use that for following these concepts on potential flows and subsequently generally all the concepts in aerodynamics. So for the stream function, the relation we have is 1 by r dou psi by dou theta is Vr, and minus dou psi by dou r is V theta. So using these two relations, one can find what the stream function of the source and sink flow is. One point that I would like to note at this juncture is that the source flow does not obey the continuity equation at the origin. You can verify this mathematically by finding the divergence of velocity at the origin. But physically as well, it's kind of intuitive because you have a point from which flow is either appearing, as in the case of source flow, or disappearing, as in the case of a sink flow. So that kind of violates the mass conservation because the mass is just disappearing into nowhere or appearing from nowhere. So that's a point that should be kept in mind. And one more thing that is important is that this flow is irrotational everywhere, and that can be ascertained by finding the curl of velocity to be 0. Now let's move on to a combination. It's a very important concept that we can combine two flows in order to get a third flow. So first let's look at what we call as the combination of the uniform flow, which we did in the previous lecture, and the source and the sink flow, which we've done today, and see what we get out of it. So let me just erase what I have on the board. So what I'm going to combine is the uniform flow and a source flow. So the uniform flow streamlines look like this, and I combine this with that of a source flow. And due to the concept of superposition, what we will get is essentially flow around a semi-infinite body. So that's the flow we would get by combining the uniform flow and the source flow. So what you actually see here is that the uniform flow starts to behave as though there was a body lying in this position, and it curves around this body, and the flow inside remains inside the body. So this becomes a separating streamline. So the flow that's outside the streamline remains outside, and the flow that's inside the streamline remains inside, and this is the separating streamline, and which gives the effect of having a semi-infinite body in the flow. So this can be mathematically analyzed by adding the either the velocity potentials of these two flows or the stream functions of these two flows, and then differentiating that in order to get the velocity fields of this flow. This is a relatively simple thing to do. What I'll right now do is something that's a little more complicated as compared to this, and once that can be done, this would be a pretty easy task to do. So I'll leave this at this. The viewers can try doing this by themselves. So now I will look at a combination of a uniform flow, a source flow, and also a sink flow. So what I'm going to do now, I'm going to add a sink flow, a source flow, and a uniform flow. The source and the sink cannot be added at the same location because they would negate each other's effect. So what I would rather do is I would add them at some distance apart from each other, which would result in a flow that looks like this. So I have the uniform flow curving around this body, and then I have a source here and I have a sink here, each separated from the origin by a distance b. The strength of the source is lambda, the strength of the sink is minus lambda, right? So what I did exactly was that to a uniform flow I added a source flow at this location and a sink flow at this location, and this led to a flow that looks like this. So this is a flow around a closed body, as against the previous case where the addition of the uniform flow and the source flow gave flow around a semi-infinite body. Here we have a flow around a finite closed body, and this is called the Rankine's oval. Right? So now let's look at the mathematics of this flow. So to start off with, I need a velocity potential or a stream function. Now I will be taking the stream function just for convenience. The stream function of the uniform flow is given as v infinity r sine theta. I am right now expressing all of this in the r theta coordinate system. I will be switching to the xy coordinate system shortly. That's the uniform flow, plus the source flow is given by 2 pi theta 1 minus by theta 2. This is of the sink and this is of the source. Now what are these theta 1 and theta 2? Let me elaborate. If I have a point P in the flow field of coordinates x comma y, and I join the point P to the point of the source, and I join the point P to the point of the sink, the angle subtended by this line with the x-axis is theta 1 and this angle is theta 2, right? So let me now express this whole equation in the xy coordinate system, because in this case it would actually be easier for me to work with that, right? So theta 1 can be written as the tan inverse of let me just name these points P, A, O and B, and I have a point C. So theta 1 is going to be tan inverse of PC divided by AC, right? So what is AC? AC is going to be the coordinate x, which is this distance OC plus an extra distance B. So it's going to be PC by AC, which is tan inverse of PC is the y coordinate y divided by AC is x plus B, this distance being x and this being B. Theta 2 similarly will be tan inverse of y by x minus B. So I will write out the stream function now in the Cartesian coordinates. V infinity r sine theta is nothing but y plus lambda by 2 pi tan inverse of y by x plus b minus tan inverse of y by x minus b, right? Now that I have the stream function, I can differentiate this to get my velocity field. Now, what is very important in a flow like this is we need to identify what these points are. These points are typically called the stagnation points. Stagnation points are points where the velocities go to zero. Now, from the symmetry of the problem, it's symmetric about the y-axis, right? It's symmetric about the x-axis, right? So, from the symmetry of the problem, we can see that the velocity v, that's the v component of the velocity, should be zero at point number 1 and point number 2. We can also derive this mathematically. So let's see how this is done. So first let's differentiate the stream function psi with respect to y so that we can get the u component. So let me just write it out on top. U is equal to dou psi by dou y, right? So if I differentiate this with respect to y, what do I get? I get v infinity plus lambda by 2 pi tan inverse of x. The derivative of tan inverse of x is 1 by 1 plus x square. Now we need to use chain rule in order to do this. So 1 by 1 plus y by x plus b the whole square into the derivative of this y by x plus b with respect to y. That's what we need, which is 1 by x plus b, and the same applying to the second term, which is 1 by 1 plus y by x minus b the whole square into 1 by x minus b. So let me just erase this. We'll write it down if we need it later. So I need to find out at what point this u velocity goes to 0. So I need to find out v infinity plus lambda by 2 pi into, I can simplify this, I can take the LCM, and what I would be left with is x plus b by x plus b whole square plus y square minus x minus b by x minus b whole square plus y square, right? So this is equal to 0 because we are looking for the stagnation point. So let me just use the argument that I had put forth a while ago. Let me by symmetry say that at points 1 and 2 the v velocity will be 0. At points 1 and 2 we know that the y coordinate is 0. So we can derive this by differentiating the stream function with respect to x and putting that to 0. But that would involve more of manipulations. But here I can argue that just from the basis of symmetry. So at y equal to 0, I'm saying that my v component, the velocity component, the y component of my velocity is 0. So I plug in y equal to 0 here to find out for what x my u velocity goes to 0. So if I plug y equal to 0, these two expressions simplify, and this x plus b by x plus b whole square becomes 1 by x plus b, and this becomes 1 by x minus b. Now on simplifying this, what I would get is v infinity plus gamma by 2 pi, sorry, lambda by 2 pi x minus b minus x minus b by x squared minus b squared equal to 0. Now here we see that x gets cancelled off and I end up with a minus 2b. Now I would take this term to the right hand side, so let me just erase this off. So I would get lambda by 2 pi into 2b is equal to x squared minus b squared into v infinity. So from here I can solve for x. X squared v infinity is equal to b squared v infinity plus lambda b by pi, and this gives me x is equal to under root b squared plus lambda b by pi v infinity. So it's at this x location that my u velocity goes to 0. At this, the u velocity goes to 0, and we already know from symmetry that for y equal to 0, the v component also goes to 0. So at these 2 points 1 and 2, this point 1 has to have the I missed a plus or minus here. So it basically means that I have 2 points 1 and 2 at which the u velocity and the v velocity go to 0. So these 2 points are stagnation points, and the streamline that passes through these 2 points is called the stagnation streamline, and it acts as a separation streamline by separating the flow outside it and the flow inside it. And this specific flow is called the flow over a Rankine's oval, as I pointed out a little while ago. So that's about this video. Let's look at some more combinations. In the next video we will be looking at a specific flow which is called the doublet flow, in which we combine these two, the source and the sink. We approach the source and sink both towards the origin, and what we try to achieve is the flow over a cylinder. So how we implement that is what we will be talking about in the next lecture. So I hope what I have covered in this lecture was clear. If you have any doubts, please feel free to contact me. So I'll see you in the next video. Thanks for watching.